Assalamu alaikum. Hello, everyone. We continue our lectures. We are in the topic of exploratory uh, data analysis. Before we start from where we left off last time, I would like to just mention something, okay? So you remember when we talked about when we have many correlated features, okay? So if there are many correlated features, then there is a room for dimensionality reduction, okay? Or at least we may need to introduce a regularizer if we are doing regression or whatever task is, we need to add regularization there in order to make sure that we don't run into the problem of overfitting. If we, to be very precise, overfitting, if we are considering many higher degree polynomials, then maybe we don't really need all of these, because if we consider all of them, we may start to capture we want to fit every sample. So then we start to more of capturing noise than following really the trend. Okay. So, and if they are linearly dependent on each other, then we may run into the problem of what is called multicollinearity. So when many features, they are very linearly related to each other, okay? They are very highly correlated and linear relation. Because in that case, we will run into the multicollinearity problem, and that can actually complicate the learning process of the model and may lead to unstable model. So in order to just to explain something here, you remember when we built these different features here, like these are linearly related to x, this is non-linearly related to x, this is x squared, okay? Though, as I said, this the person's correlation may not capture, and sometimes may not capture the nonlinear dependency, but for this specific example, the values are all positive. It's actually capturing the nonlinear dependency. So there, if you look here, for example, C5 is it no C6? Sorry, C6 is non-linearly dependent or related to X, and the correlation between the height and C6 is so high. Okay, it's still captured. So there is high correlation between C6 and the height, but this is not like C6 is not linearly related to height. So sometimes, like if you want to remove very correlated features to each other manually, you may actually that may not be the right thing to do. Sometimes maybe you need to plot the scatter plot. You make sure that is it multi-collinearity? Is it like you have many features where they are very linear related to each other, or this is actually non-linearly related to that, and you may need it in order to go beyond a linear line. You may need to build a curve. Then maybe you need to keep that, okay? And regularization can always fix overfitting problems if you are going beyond linear lines. So the bottom line, if you see like many correlated features, then maybe look at the scatter plot and see if the relation is nonlinear. You may not remove those manually, keep them, and the regularizer will actually, as we will, I don't want to be ahead of the materials, because we're going to come to the regularization next topic when we talk about linear regression. Regularization can help solving the issue of overfitting and bring kill some features and bring their weights to be 0 or very low. Okay, and if there is multicollinearity, then you may remove that manually, or you also can leave that to the regularization. And we're going to come to more details about this later on. I just wanted to highlight that. So in some cases, there could be correlation, but the high correlation doesn't always really mean that is only linear dependency is there, because sometimes it could be nonlinear dependency, and in some cases this correlation can capture the nonlinear dependency, as it's the case here, because all of the values here for the height are positive. So as x increases, x squared will always increase. Okay, but in some cases, as I said, the person's correlation may not capture the correlation, okay? So then scatter plot is always useful. So scatter plot with the correlation can tell you the whole, more complete story. For example, here, y is equal to x squared, okay? So there is a dependency here, but the correlation is not capturing that, okay? So we see like the correlation here is between them is 0. But if you plot the scatter plot as we see here, you see there is a relation actually, okay? So anyways, that's it about this. I wanted to make this note before we start today's lecture. Let's start from where we left off last time. So here, so we are at the first case study here. We're working with the principal component analysis. So we have this data here, okay? So let's print the data and look at it, okay? Okay, let me first restart the kernel, okay? Okay. So we run this cell. This is the data. This is our data. Okay. So we have two categorical attributes and we have a number of numerical attributes. Okay. So this is like about cars. So for each car, the origin, the car name, the model year, the number of cylinders, the displacement, the horsepower, the weight, acceleration, and mile per gallon, and economy. So economy is a class, okay? 0 is means like this car is not economy. It's not it's less economy. So 1 is medium economy and 2 is very high economic car, okay? So these are the classes, okay? This will be our target variable economy. So we wanna actually build a model, okay? Like given these input features, all these input features, we wanna predict if the car belongs to class 1 or 0 or 2 in terms of the economy class, okay? So yeah, so here we print the info, so there is no missing data, okay? Things are okay here, okay? So then let's keep going. We don't need to say much here. Let's come here. So here, okay. So for this example, okay. So as I said, if I'm doing things towards building a model, I prefer to do everything things in a sequence. In the sequence I explained in the. If go and look into my video for the guidelines for the final project. Okay. So I prefer to do feature transformation, normalization, everything. And then I do principal, do exploratory analysis, including correlation and principal component analysis. But here, let's just follow the whatever in the slides here. So this is for the sake of the explanation. So here, what we are doing, we are actually excluding the object or the categorical attributes. We are only extracting the numerical attributes, and then we are computing the principal component analysis for those attributes, of course, after we're dropping the last column, which is our target. We don't include the target variable in the computation of the PCA. So here we are excluding these. This could be important, okay? That's why I'm saying usually the way it should be done is you do this transformation first and normalization and everything, and then you look into the exploratory analysis, because actually origin could be very important, like factor or attribute in deciding what class the car belongs to, as well as the car model itself. Okay, some models are like less economy than others. Okay, but anyways, for now we are excluding them, and we are working with the non-scaled uh, attributes. As you can see here, the numbers are coming from very different scales. The weight is very high here, okay, compared to other, like the values of cylinders and so on, okay? So they are at different scales, okay? But let's follow the slides, okay? So here we have selected the numerical attributes, and then we are computing the principal. Here we are just defining like which columns we are going to include in the computation of the PCA. As I said, we are dropping the economy because economy is the target variable. It's the class we should include in the computation of the principal components, because later on we don't have the economy. We want to predict the economy, so we shouldn't use it to build the PCA. Okay, remember here, our goal is to come up with a compressed set of the features. We're gonna actually do dimensionality reduction. So here we have 7D, right? 1, 2, 3, 4, 5, 6, 7, but after excluding the categorical attributes. So every point here lives in 7D, but we are gonna project it into much lower dimensional space, okay? So in fact, here we are considering only two components. So we're going to move from 7D to 2D, okay? So we from scikit-learn dot decomposition, we import PCA, and then here we create our object, PCA object, okay? So we're creating one instance from this class PCA, and we're passing the number of components we need. So here we are only considering the first two components, okay? So here we create the PCA, and here we actually do the actual fit and transformation. As you can see, it's a one function, okay? So you remember when we used to do normalization, here I have this commented code here, okay? So here we create the scalar, okay? So we create the object here. It's one instance from this class, and here we fit that in our data. So what we are doing here, actually, we are computing the parameters that are needed for the transformation. For min-max, the parameters are the min and the max based on our data. From our data, for each column, it has its own min and max. And here we perform the actual transformation, okay? So this function can do both at the same time. So it will fit and transform. It will compute the required parameters. So what are the parameters for this case? For the principal component analysis, the parameters are the weights, okay? So because every principal component is a weighted sum like of the original features. So we're finding that those weights, and then we perform the transformation. So the first weight times the first feature plus, and so these weights are the elements of the unit vector U, right? Okay, that's it. So here we perform the transformation, then we can access the component, different components. The outcome of this is a NumPy array. So for this case, it's a 2D NumPy array. Then we are accessing this is the first principal component, which is the elements of the first column, okay, and this is the second PCA, which are the elements of the second column. So these are the principal components, okay. So it's a 2D array. Then we are actually, what we are doing here, we are creating two new columns in our data frame, where the first column is equal to the first principal component, and the second column is equal to the second principal component, okay. Yes. One thing to mention here, okay. So this example is a bit confusing because actually this is adding the features to the same data frame. But actually, when we perform principal component analysis, we are actually moving from the old features to the new features. We're not going to use the old features anymore for our analysis, okay, for building the model. So we're going to use the new ones, okay. So they should be like a new data frame, but that's fine. Just you need to be aware of that, okay. So we're not going to be using we're not going to be adding these as more features. No, we are moving from the original features to these two features, okay? Let's look at that. Okay, so these are the two new features, okay? So now what we should have is like the target variable and the two input features. We can build model from these two features to predict that. So we're not going to add these as extra features on top of what we have. No, that's not the case, okay? And as you can see here, this is the first principal component. This is nothing but some weight times this value here, 70 plus another weight times 8, and so on. So as you can see, every one of these features, you can relate it to like a physical feature you have here. For example, here, the year, the model year. Here, the number of cylinders, 8, 7. But here, actually, this number, physically, you cannot come up with a meaning for it because it's a weighted sum of all of these, okay? So it has no like physical meaning, okay? Yeah, so yeah, that's it for this cell. Yes, let's keep going now. We have these two features, Okay, now we want to see like how much variance every one of these is capturing, BCA1 and BCA2 from the original variance and from the variance in the data. Okay, the variation in the data, the original data. Okay, so then we can actually call this this property or attribute inside BCA. Remember, BCA is an object. Okay, so it has attributes as well as functions you can run on it. Okay, so it's a BCA object. Okay, so we call this attribute or property explained variance ratio, and I think this is a list, so that's why we call function enumerate in order to iterate over the index and the value for every one of them, and we see like how much variance each one of these BCAs is covering. It's very interesting here. We can see like BCA1 covers more than 99.75% of the variance in the data. Okay, and the other one is covering 0.21% of the variance. Okay, so actually there is so much redundancy here. All of these features are very correlated to each other. Okay, original features here, they are very correlated. We don't really need all of these features to predict the economy. Okay, so and in fact, it makes sense, right? Like for example, here the number of cylinders, the displacement, which defines the acceleration, the horsepower, the weight, okay, the mile per gallon, okay. So all of these features, like they're very like maybe one of them is enough to tell if the car is is economic or not, okay, if it belongs to class 0 or 1 or 2, okay. So but anyways, let's yeah, so there is so much redundancy here. Let me do something else. Let me actually pass here this equal to 7, okay, instead of 2, and run again. You see, like the first 3 principal components, okay, cover the whole variance, okay. So like I don't, the value is exactly zero for the remaining 4. So though these points live in 7D space, okay, but actually they live in a much smaller subspace than 7D, okay. They live in only 3D space inside that 7D. Let me go back to this. Put this 2, okay, and keep going. So here are we are printing out the BCA components. So this is for the first BCA. Now I'm back to only 2 components, okay? Only 2. These are the weights, okay? So these are the weights of the first BCA, and these are the weights of the second BCA. If you are building a model, you need to store these weights, because later on when you receive a new sample, you will receive the original data. Okay, so if your model is built based on taking BCAs as input, then if you receive a new sample, you need to weight it with these weights. The first element here, the model year times this plus the second times this, and so you convert it, you compute, you project your data point into the same principal directions. You come up with these 2 values and you feed them to your model. Okay, then you predict the economy. So if you're building your model based on the BCAs, then you have to save these weights, and every point you receive after that in the operation phase, you need to weight it with those weights, with the same weights here. Okay, so now let's rank these weights let's relate them to their input attributes, and rank those attributes based on the highest coefficient. We call them coefficients as well here. So we're gonna compute these BCA coefficients. We have already printed them out here. Here we're rounding them. This is for the first principal component. We are focusing on the first principal component. So we are rounding those values, and we are creating a list. Okay, so we have 2 lists here. The list, we know this by now, okay? We have the list of the columns, the numerical columns that are used for the BCA. So all the numerical columns except the economy and their coefficients. So from these 2 lists, we're creating a collection of tables using zip function. Then we cast it as a list. Okay, this is our list. Okay, now we are creating a new data frame. Okay, from the content of this list, where the columns are the field or the input attribute and the coefficient. Field is taken, the first field is the first value in this top. Sorry, now it became list. Okay, so it's a list of tuples. So the first tuple will be the field and the second will be the coefficient, and then we are sorting the values using in this data frame by the coefficient in ascending order. Sorry, in descending order. Okay, ascending is equal to false. This is what we get here. Okay, so you can see weight has the highest coefficient, then displacement, then horsepower. Be careful, like this, like it's in, like it's the lowest one because it's negative. Okay, so if this is like negative 0.9, then it's still very high correlation. It doesn't mean like it's less correlation here. Okay, but these are the coefficients. As you can see here, like the weight is 0.99, almost one, and everyone else is almost zero. Okay, so the weight is actually specifying the first BCA, and it's covering 90.9.75% of the variation. Okay, so that is interesting. Okay, here I feel like, as I said, many of them here can be used. One feature of this is enough because many, as I said, the mile per gallon, the horsepower, the acceleration, the displacement, all of these, the number of cylinders, each one of them can be actually used. Okay, they are very highly correlated. The weight is chosen here. Okay, the weight is chosen, but actually the weight has been chosen because it has the highest values here. It's dominating because of its highest values. It's not like I think they are all equally important. Okay, it's just dominating because the values are very high. Okay, so in fact, I can show that I actually added this here. Okay, and I commented it. If I here, if I normalize all of them, then I may see different results. Okay, because as I said, all of them are equally important here. Let me run again after the normalization and to look at that together. Okay, so now you see now how much first and second BCA covers is different. Okay, okay, and here, yes, you see now the number of cylinders has higher coefficient. Okay, or weight. Then the displacement, then the weight comes after that. So one, two, like of them here, they are very close. Okay, as I said, when we normalized them, the weights are like very not far away from each other. This is mile per gallon is actually it's inversely proportional. That's why we have negative sign here. Okay, it also affects the economy. So after the normalization, you can see the weights are very close. Maybe these are very low. Some will be very low, as I said, will be low compared to others because you're gonna pick some of them. Okay, the model will pick some of these. But yeah, that's these are the weights now after the normalization, and I think we will stop here for today, and we will continue next time, inshallah. Thanks for watching.